In this first example, we're told that a ball is launched straight up at 50 meters per second from ground level. And we're asked a bunch of questions. What's the maximum altitude it reaches? How long will it take to reach this altitude? How long will it take to hit the ground? How fast will it be going when it hits? Now, this is a physics problem. And you might be tempted, if you've had some physics, to go out and try to Google physics formulas, but don't do it. What I'm going to show you today is how you can get all of this information from the graph of velocity. So the first thing we need whenever we're dealing with the physics of motion is we need some sort of frame of reference, okay? Because we have to measure displacement and with respect to a fixed point, and we have to have some idea of what direction is positive and what direction is negative. So what I'm going to do is I'm going to take ground level to be 0. And then we're going to measure the distance from the Earth, okay, from ground level. And we're going to call up positive. All right, so the positive direction is up, negative direction is down. That seems like a pretty logical frame of reference. So we're also told that the force of gravity is accelerating this object toward the Earth at 10 meters per second per second. So remember, acceleration is the rate of change of velocity over time, right? So what this is saying is that the velocity is changing by 10 meters per second every second, but that acceleration is happening toward the Earth. And given our frame of reference, toward the Earth is in the negative direction. So we've got an acceleration of negative 10 meters per second squared, or meters per second per second. All right, so all that's telling us is that, if we're starting out here at 50, then after 1 second, we're going to subtract 10 meters per second from its velocity, right? Its velocity is changing by 10 meters per second every second in the negative direction because it's being pulled down toward the Earth. All right, and that makes sense. If you think about how a ball, you've thrown balls up into the air and probably caught them, and you know what's going to happen, right? You toss it up into the air, it goes up, 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 and eventually it slows down as it's going up, right? And eventually stops, turns around, and comes back down, and then you can catch it, right? So that's what we expect to happen, right? You know exactly what's going to happen. So we can graph this velocity. We can graph the velocity versus time here, and we just know that every second the velocity is less by 10 meters per second. Now, the actual number is 9.8 meters per second. That's what you would use if you were actually doing physics here. But we're just going to take 10 just because it's easy. It makes the problem easy, and I just want you to get the concept. So we're just going to subtract 10 meters per second from the velocity every second. Okay? So this is the upward phase of you can see the velocity is going down, but this is the upward phase of the toss, right? Even though the velocity is going, it's slower. It's it's going up, but it's slowing down, right? And then until it gets to a point where it's 0. Okay. So all of this, during all of this time, when the velocity is in the upward direction, the ball is going up, and then it hits 0. And what's going to happen? It's gonna fall back down, right? So now it starts moving in the negative direction, right? Now the velocity is negative, right? That just means it's coming back down toward the Earth, which is what you'd expect, right? And so now this distance here that it's covering is in the negative direction, right? It's falling back down toward the Earth. We took our frame of reference to be up. And so we're just subtracting 10 meters per second every second, all right? Until what? Until it hits the Earth, right? We're assuming that it's just going to end up back where it started, right? So after it's covered the same amount of distance down as it did up, then it's going to hit the Earth. And so we can graph this velocity curve, right? We've got a bunch of points here. We just connect those points, and that is our graph of velocity. And remember that the distance is the area under the velocity curve, okay? And we can figure out that distance. We can figure out that distance by looking at the area. So let's look at the upward phase of the ball's motion first, right? The upward phase is all of this time when the velocity is positive, meaning that it's moving away from, or it's moving up, it's moving away from the Earth. Up is positive, right? It's moving away from the Earth, and so its distance is increasing. And so this is all positive area, which means positive distance. This is just a triangle, right? This is a triangle that's 50 units high and then 5 wide, right? 5 seconds wide here. And so 1/2 base times height gives us 125 meters. So we've answered the first question. What is the maximum altitude it reaches? 125 meters. Okay. How long did it take to get to that point? It took 5 seconds. All right. Now after it goes up as high as it's going to go, right? That's the point where the velocity is 0. So that's this point right here. The velocity is 0. And now it's coming back down toward the Earth. Okay, so the velocity is negative, meaning it's traveling in the negative direction, which is back down toward the Earth. So downward direction. And we can only travel down as far as we went up, assuming that the ground level doesn't change, right? So, or we're not throwing it off a cliff. That's so we're just gonna, it's just gonna go up and it's gonna fall back to the ground right where it started. And so, once it has covered once it's covered the same distance in the downward direction as it did in the upward direction, then it'll hit the ground. So you can see we have another triangle here. This downward, the portion of the velocity curve that's negative is downward distance, and the area here, if I go out to 10 seconds, is a negative 125 meters, right? So that's 125 meters back down toward the Earth. And so that's when the ball is going to hit the ground, right? After 10 seconds. So there we have the next question answered. How long will it take to hit the ground? It'll take 10 seconds. How fast will it be going after that 10 seconds? Well, we can look and see what the velocity was, right? We can look here. It looks like it's going to be a negative 50 meters per second, right? That means it's traveling 50 meters per second downward, and it's going to hit the ground at 50 meters per second. Okay, so we've answered all the questions. So there's just a few things I want to point out to you. So one is that the total displacement is 0, right? The ball ends up exactly where it started, but the distance traveled is actually 250 meters because it went up by 125 meters and then back down by 125 meters. Now the other idea is this idea of negative area. You can see that we've got negative area here. All right, so we're considering that to be negative area. But all that really is telling you is the direction of motion, right? We've got a frame of reference and we've called down negative. So this just means that the change in the distance over this time period represented by the negative area is downward, okay? Now the last thing I wanted to do is just plot this distance over time to show you what this looks like. So we've already found that it reaches its maximum altitude at 5 seconds, and the altitude is 125 meters. Okay, that's just given by that first half of the area under the velocity curve. All right. So, but you can actually plot this distance, and it's a nonlinear function. Even though the velocity is linear, the distance is nonlinear. So you could just find the areas of each one of these segments. So like, for example, let me pick up a different pen here. If I want to know the area over the first 2 seconds, it's just this trapezoid here. And I can find the area of that trapezoid. I can find the distance after 2 seconds will just be the average of the bases, right? So 1/2 um, and of 1/2 of the sum of the two bases. So 50 plus 30, and then it's two units wide, right? So that's essentially the height of the trapezoid. And so you can see that the distance would be 80. Okay, so we could plot that distance at 80. So 80 is about, let's see, there's 75, so let's say that's 80. Okay, and we could also plot the velocity at 4 seconds, and so on. So I've calculated some more distances here and plotted this trajectory. All right, so I've plotted the distance traveled over time. And you can see it's this nice parabolic shape, which is kind of what you'd expect. So, it's, and you can kind of see that, okay, once you hit 125 meters, then, this area here and this area here are going to cancel each other out. You start subtracting area and you get this nice symmetric curve. And so I just think that's interesting that we don't need any of those physics formulas that you may have learned if you took physics. You can get all this information straight from the velocity curve. The beauty of it. All right, so I guess maybe what I should do at last but not least is just summarize the answer to the question. So what we found is that the ball reaches a maximum altitude of 125 meters after 5 seconds, and it hits the ground at 50 meters per second after 10 seconds. Okay, and we figured all of that out from the velocity curve.